Okay, so let me remind you, last time we defined, we said that a knot is of genus less than or equal to G if it can be presented as the boundary of a genus G surface with one boundary component, a sigma G1. And by the way, the standard way to say it is to say if it bounds such a surface. And we also defined, and here we haven't even shown yet that every knot has a genus, right? So the genus is the minimal G for which this is possible, and we haven't yet shown that every knot has a genus. And then, so that's one of the tasks for today. And the other definition from last time was that we said that a knot is ribbon if it's the boundary of a disk with ribbon singularities, but no clasp singularities. So here I should have added a singular disk. So I'm allowing singularities. But I'm allowing this type of singularity, yet not that type. Okay? And maybe before I go to the main task, so the main task for today will be to show, or maybe also next time, to show that these two properties can be reformulated in terms of tangles. And this is sort of to support why I really care about tangles. I gave you, one is for faster computations, but there are also topological questions that you can answer with tangles, or that you can at least reformulate in terms of tangles and then perhaps answer. So that will be later today. But before that, I want to give yet another definition, and I want to give it very, very briefly and state and say one word about it. And this is the following. So definition. So a knot is a slice or smoothly slice if it can be presented as the boundary in S3. So I'll think of knot as lying instead of R3 as lying in S3. It's the same. So if it can be presented as the boundary in S3 of a smooth disk in the four-dimensional ball in B4. So in other words, here's the picture. So if this is S3 and up above is the four-dimensional ball B4, then a knot is called slice if you can find a two-dimensional disk. Well, I'm drawing it one dimension down, so it looks like an arc, but it's really a two-dimensional disk, whose boundary, so the boundary of, embedded in the four-dimensional ball, and whose boundary in the three-dimensional sphere is our knot. Okay? I'm not going to say much about it, except the following. So it is easy to show that if a knot is ribbon, then it is slice. So let's call it proposition. I don't know, it's somewhere above a claim and below it, I don't know. It's hardly worth it to call it a theorem. Okay, so why is this true? Why is a ribbon not always slice? So suppose, so basically what you do is you take the ribbon disk. So you take the disk whose boundary is the knot, and you push it in its interior into the ball. Okay, so you you take the disk and you push its interior, you push everything here into the four-dimensional ball. So basically, if you think of the four-dimensional ball as, if you write it as, instead of ball and sphere, you think of it as the three-dimensional space, and the upper half of the four-dimensional space, or lower half of the four-dimensional space, then you basically let this disk fall into the lower half. So you let t, the fourth coordinate, go down as you go farther away from the boundary. But you do it in such a way that wherever you have a ribbon singularity, the horizontal side falls deeper than the vertical side. And then they don't intersect. Sorry, a smooth non-singular disk, of course I meant. Okay? So again, you push this band down in R4. You push the inside of that band also down, but less. And then they don't intersect. Okay? You cannot do it with a clasp singularity. If you have a clasp singularity, well, I mean, you can push this part down and you can push this part down, but by the intermediate value theorem, somewhere along this line, they will be pushed equally far down. Okay. So it's obvious that the ribbon knot is sliced. The other direction is not known. So conjecture, well, it's called the ribbon slice conjecture, but it's usually formulated as ribbon is equal to slice. Okay? Except most people don't believe it and think that slice does not imply ribbon. So let me formulate it this way. Conjecture, slice does not imply ribbon. And how would you prove this conjecture? So you would prove this conjecture by finding a slice knot, which is not ribbon. Well, there are proposals. So there are specific proposals for knots. In fact, the GST 48 is known to be slice, but not known to be ribbon. So how do you know that it is slice? In principle, it's easy. In principle, you just draw it in R4, in R4, okay? So, but then how do you show that it's not ribbon? Well, to show that it's not ribbon, you have to show that you cannot find a surface that has some property, which means that you have to go through all surfaces in the world, and there might be many. So that's in principle difficult. And I will be, and that's why I care about formulating the ribbon property, or playing with the ribbon property, formulate it in terms of tangles, showing properties of these, constructing appropriate invariants of all of these tangles. It's basically all because of that. And again, my goal really is not to show that things are ribbon, but to show that things are not ribbon. Okay. Okay, good. So, so now I want to start reformulating these things in terms of tangles, but I think I should do a little bit of further stuff about surfaces first. Okay, so forgive me if I insult you. Okay? So by doing things that are too elementary. So, you know, maybe I'll start with so, you know, yeah, so maybe I'll remind you that we already found a Seifert surface for the trefoil knot. And it was, well, you take this disk inside, and you take the disk outside, and you connect them with 3 twisted bands. By the way, this is completely equivalent to drawing the following picture. So first of all, here is another picture of the trefoil knot. So you take 3 crossings and you connect them this way. Okay? And then this picture is the same as that. So you take 2 discs and you connect them again with 3 twisted bands. Okay? So, you know, if the discs were colored, this will be the white color and this will be the black color. And each twisted band is twisted, so this remains an oriented surface. It remains a surface with 2 colors on the 2 sides. Anyway, what's not obvious is that this is, in fact, the boundary of a surface, of a sigma G1. If you know the classification theorem of surfaces, and you know it, but it's actually not visibly obvious, so I want to go through this. Okay? And if you look at the handouts that I distributed last time, so there were 8 pictures of Cyphered surfaces on it, and it's not at all obvious that they fit this sort of simplified picture. Okay? Okay, so I have a bunch of claims. So claim number 1, I claim that sigma G1, which is also known as, you know, let me do it differently. So I claim that sigma G1, which is a genus 1 surface with 1 boundary component, or maybe just a torus with a disk removed. So I claim that this is homeomorphic to a thickened camel. Here's a camel. Is this how you say camel? Camel? Camel. Right, sorry. Here's a camel. It has 2 humps. And when I say thickened, I mean, let's do tau of this. Tau is the thickening map. And the thickening map will turn it into, so each line here becomes a band, and well, including the line at the bottom, so the line at the bottom would look like this, and this is clearly a surface with circle boundary, right? You just trace around the boundary and it's a circle, and well, it's clearly a surface, and I claim that it's that one. Okay? By the way, I said replace it with bands. In a sense, you should remember that the more natural type of knots to think of are knotted bands. So in a way, they always were bands, okay? If you are thinking more naturally. Okay. Anyway, well, except this isn't a knot. This is a graph. This is a, okay? Anyway, proof. So what's this? Well, it's a torus with a disk removed. But so what's a torus? A torus is when you take a square and identify sides as indicated here. I hope this is all familiar, right? I think this is in the common knowledge of every mathematician. And then I have to remove a disk. So I have to remove a disk somewhere. So I'm indicating the disk that I'm removing. But there is a better disk to remove. Not this one, but another one. The one I want to remove is this one. So take the center of the disk to be the corner of that square. But you see, in this square you identify top to bottom, so this point is also the same as that, and left to right, so this point is also the same as that, and that point is the same as that. So the point is really this, 4 points, drawn as 4. It's just 1 point. And then let's take a disk centered at that point. So a disk centered at that point would be, well, you remove everything that's close to it. So you remove this corner, and that corner, and that corner, and that corner. But this is the same as, so you see, instead of removing just the corner, let me remove a large corner. Okay? So let me remove this on the left, upper left, this on the upper right, this on the lower left, and this on the lower right. Sorry, I'm removing this, removing that, removing that, removing that. So what remains is to glue this to that, and this to that.
Oh.
Yeah?
This is the nicest thing I've seen.
Okay.
Okay. Oh my god.
Okay, good. But now what is this? So now I took like a different disk, a disk in the center, and took a band from the left and a band from the right and connected the two, and a band from the bottom and a band from the top and connected the two. But that's exactly that. So this disk here, the blue disk is here, this blue disk is this blue disk, and I took one band and connected it and another band and connected it. That's exactly that. Okay, so this is equal to that, and we're done. Okay? Good. Second claim. So I claim that a genus G thing, well, a thing like that, well, I'll claim it with G, but draw it with 3. Okay? So I claim that sigma 3,1 is isomorphic to, or homomorphic to the thickening of a caravan of 3 camels. So camel 1, camel 2, and camel 3. And of course, I mean it in more generally, right? So proof, so let me draw this in a slightly different way. So first of all, let me, instead of putting the disk on the right like I just did, let me put it on the top. So, so here is the picture. Here are the 3 holes, and I'm removing this disk up there. Okay? But now let me write it in yet another, in yet a different way. So I can write it as 3 tori with holes, but connect their edges with band. So connect this edge to that edge with band, and this edge to that edge with band. You see, if you will, gee, I was just at the dentist. So they did it to me. Sorry, I'll remove my mask very briefly. In fact, I'm allowed. So, you know, they put this gadget in your mouth. They all, like, force it open. So sorry for this awful thinking that goes in my mind. But you do this to that opening. You force it open all the way around, and then basically, you know, you open it further down to here, and also in the back, you kind of force it to open further, and then basically then you have 3 pictures like that, connected with just thin bands. Okay? And what is this? This is just 3 of those connected with 3 bands. So I could write it as 1, sorry, 1, what have I done? 1, sorry, okay, 1, and then a second 1, this was, yeah, and then a second one, and then I connect them with a band, and then a third. But that's exactly the thickening of a 2-hump count, 3-hump count. QED. Okay, next claim. Any graph, if you thicken it, you get a sigma gn. So the thickening of any graph is a sigma gn. So, sorry, and I should be even clearer, any thickening of any graph. So why do I say any? So first of all, what do I mean by a thickening of a graph? So a graph has vertices, sorry, any orientable thickening is a sigma gn. So a graph has vertices, so you can thicken the vertices to things like this. And a graph has edges. Oh, and by the way, this depends on choosing a cyclic ordering of the edges. So, so that's why the word any. Okay? And then a graph has edges, so you can thicken every edge to either this or that. So you can thicken it either with a twist or without a twist, or with 17 twists if you wish. It's the same. I mean, basically only the parity matters. So the claim is that the thickening of any graph or any orientable graph is a sigma g n, right? Proof. Okay. So, sorry, I keep missing conditions. So any connected graph. If it's not connected, you'll get a disjoint union of several such things. So proof, you know what, no, let me go back to earlier board. So proof. Okay, first of all, suppose you have two vertices connected by an edge. Since then you thicken this. So the thickening of this is equal to the thickening of. So you see, if you thicken this, this becomes a band, and here you have other bands connected to it. You can take one of those bands and slide the place where it's connected. You can just slide it all the way to here. If this was twisted, it doesn't matter. You could still slide it, and it would connect, and then you'd slide its end to this side instead of that side. But whatever you do, you can slide an edge from one vertex to another vertex. Okay? So the thickening of this is equal to the thickening of, I'll be schematic. Instead of having 3 on each side, it will become 3 and 2. Okay? Fine, you can continue this process. You can slide the next, slide the next, slide the next, until, so eventually you'll get, basically until the vertex disappears. Right? If you slide the one before the last, there is simply no vertex here anymore, or you can cancel that vertex. So this will become the thickening of 1, 2, 3, 4, and the fifth goes there, and that's it. But this way you can cancel vertices. So therefore, the thickening of any graph, any thickening of any original graph, can be written as a thickening of a graph with a single vertex. Because you can always push all the edges to just one vertex, yes?
So does the slider merge into one of the other sliding series? Because I thought it should be, say, 6 here.
Did I miscount? So 4, 2. Oh yeah, you're right. I miscounted. Of course, the number of ends at the end disconnects to somewhere outside, so the number of ends must be the same. So you can write anything as a thickening of a single edge. Okay? A graph with a single vertex. So a graph with a single vertex is a thing like that. But you see, the edges are cyclically ordered. So, well, a thing like that. But this is the same. So you see, replace this single edge by a little disk. And this is the same as saying that I'm taking a coupon. So the disk here becomes the coupon. And I'm connecting things on top of it in some order. Okay? So my conclusion, and this is what I really wanted, I didn't want the single vertex, I wanted a single line. So the thickening of any graph is equal to the thickening of a single edge with chords drawn on top. Okay? Now, these edges can no longer be twisted. Because if any one of these edges was twisted, you'd be ending connecting the black side of the coupon to the white side of the coupon. And my assumption was that it's orientable. If I wanted to generalize a bit and write a statement with non-orientable, I could. But I don't. Okay? But at the moment, these edges are no longer twisted. Okay. So now, suppose in this graph there was a canal configuration.
Sorry, are we saying they're not twisted at all? Or
Well, they're twisted an even number of times. I mean, I'm looking at the topology. I'm not looking at it as an embedded thing. I'm looking at it just as a topological space. So twisting an even number of times is the same as not twisting at all. Though, by the way, yeah, okay, never mind. So now, suppose somewhere within that graph, I find a configuration like this. So somewhere, so this graph is made of a base, and then, so I don't know, base and chords, and suppose two of the chords intersect. Okay? Then, but of course there could be more. So there could be more chords connecting like this, or from here to, I don't know, there could be more chords. But if you just thicken these chords, you get, well, you get the usual picture. And the other chords are connected to here, 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 well, to any of the remaining places. But now, look at the boundary of the thing I had here. It's a connected boundary, right? If I look at the boundary, I can trace it, and it's a single thing. Which means that, say there was something connected to here, say there was an edge connected to here, I could slide it to connect to here. And then I could slide the next one, and so on. And then if there was an edge connected to here, I could slide it to here, and then along this and out. Basically, I can slide all the other edges out. So the thickening of this, if it has a crossing, then two chords can be factored out. So I can factor out two chords, and I'll be left with whatever is left. Okay? But then I can continue, and if there is a crossing here, I can slide it out. I can factor it out. So basically I'll get a caravan of two hump camels, and then a crossingless situation. Now, take an innermost take an innermost camel here, cord here, and just slide everything on top of it outside. So you factored it out. So you can continue, and you'll get a caravan of 200 camels, followed by, well, again, I can slide out a small, the smallest camel. So followed by a camel, followed by another thing, by the rest. But then I can continue. So basically, I'll just get a caravan with a number of 2-hump camels and a number of single-hump camels. So you can check that if you have G of Z's and maybe I will call it G2, no, G of Z's and N of Z's, then this is a sigma G, probably N plus 1. So basically, each single hump camel, when thickened, becomes it creates a disk boundary. And that's all it does. QED. So now, if we look back at the trefoil knot, say, so a different way to view the trefoil knot is to say we have these 2 disks and they are connected with 3 bands. So this is really a thickening of a graph with 2 vertices and 3 twisted bands. Well, actually, I've shown that already. Okay? But that's one of the graphs that it's orientable. It's one of the graphs that we consider. It has a single boundary component, so it's equal to sigma G1, sigma Gn for some n, sigma G1, because it has just one boundary component, so it's equal to some sigma G1, and that's all I wanted to show. But by the way, and if you look at any of the 8 examples shown here, it's very easy to show that each one of them can be written as a graph with bands connecting. So a graph made of disks with bands connecting them. So each of these is just a sigma G1. So you know, it also follows from the classification theorem of surfaces. And essentially, I've proven it here. I've proven the combinatorial side of it. Okay. What else did I want to say? Yeah, well, okay. We still have to show that every node is the boundary of the Seifert surface. So theorem, every K is bounds a Cyphered surface. That's a completely different story. So how do you do it? Well, let me let me do it to the trefoil and then explain how to do it in general. So first of all, you orient the knot, and then you consider its oriented smoothing. So when we talked about the Kaufman bracket, we talked about every crossing can be smoothed in 2 ways. But only one of these 2 ways respects the orientation. So in other words, if you have a crossing then you can smooth it this way, but then that doesn't respect the orientation because you will not be able to orient the top line nor the bottom line. Their orientation clashes. However, this orientation, this smoothing, does respect the smoothing. So use the oriented smoothing, or the smoothing that does respect the orientation. In the case of the trefoil, this will give you a picture like this. Now, in general, you will be getting a different planar picture, but so if you start from a bigger knot, you'll get a more complicated planar picture, but it will be made of cycles that are oriented, and that every time they come near each other, their orientations are consistent, so this would have to be oriented this way, so this would have to be, so this is actually not a good picture. So every time they come next to each other, so wait, if this is oriented this way, then this one has to be oriented that way. Well, okay, a picture like this, there could be more cycles. And they could be nested in more complicated ways. This goes this way, then this goes that way. Okay? So replace this. Oh, so these cycles are called, so each of these cycles is called a Seifert cycle. So now think of a lily pond. Do you know what are lily ponds? So a pond with these lilies. So basically replace each of these cycles by a disk. But think of these disks as having their edges, as lying mostly below the water, but having their edges coming up a little bit. And if they are nested, put the biggest lily lying below all the others. And okay, so in other words, maybe I'll do it in the simplest example. So in the simplest example, which is this one, you'll have like a big disk sunken a bit, and inside it a smaller one which sinks a bit less to down below the surface. Okay? Now this is now an embedded union of disks. Embedded, they don't intersect because the outer one go below the surface deeper. Okay? Now let's try to reconstruct the knot. So how do you reconstruct the knot? So this diagram was obtained from the knot by replacing every crossing by a smoothing. So now what I have to do is, wherever I see a smoothing, wherever I see a near tangency of two cycles, I need to replace it by a crossing. How do I replace it by a crossing? Oh, I'm stupid. I have the perfect gadget in my office to demonstrate it, but I forgot to bring it. But basically, so you have those two lily cups. You have these two cups next to each other, or maybe nested inside each other. It doesn't even matter. Because they have their two edges, they're two edges next to each other. Connect these two edges with a twisted band. So take a twisted band and connect it from one edge to the next. Sorry for my limited, insufficient preparation. But you see, a twisted band, when looked from above, is exactly a crossing. So basically, each of these is just a twisted band. Now, each of these disks, so each of the Seifert cycles bounds a disk, and all of these disks have a natural orientation because they inherit an orientation from the boundary. And all the boundaries were oriented. So all of these disks are oriented. They are connected with twisted bands, and you can check that this means that the orientation is respected, that the bands respect the orientation, so you get an orientable surface. Finally, topologically, what is this surface? So each of these disks, topologically, is just a small circle, and each of these bands, twisted bands, is just an edge, maybe with a twist. Well, all of them have twists on it, but it's an edge with a twist. Okay? So topologically, you just got a graph with twisted bands connecting it, and that falls into the theorem before. So this is isomorphic to some sigma G1. Homeomorphic to some sigma G1. Are you okay? Yeah, that wasn't the best show ever, but I'm sorry about that. Okay, what's next? Oh my God, I tore apart my class notes. Now I don't know what to do next. Yeah, one more thing. And this will have to continue next time. But I thought it would, so it's okay. So now, actually, this is going to be on your homework assignment. This homework assignment. So suppose you have this. We already know that it's homeomorphic to that. Right? This means, as an aside, so, over this one, I can mark a core. The core is the thing whose thickening, core is kind of the opposite of thickening. So the thing whose thickening was the surface is what I would call the core. So in fact, the surface is homotopically equivalent to its core. You can retract the surface to its core. So this is the core. So your homework, one of the questions on the homework assignment, well, if these two are the same, you ought to be able to draw the core here as well. So the question will be, what's the core? What does the core look like here? It's a drawing question. Okay? Whichever it is, it's something. I don't know. Something. Well, no, I go out of the surface. Something, okay? Whichever thing it is, you can shrink the surface. No, I don't have time to say what I wanted to say. I'll skip it. So I'll stop here, but next time I'll explain the relationship with tangles. Okay, so next time I will tell you that from this it follows easily that everything can be defined in terms of tangles. Sorry, I've gone too slow today. So see you on Monday.